Hi, in this video, we're going to introduce thermodynamics. Thermodynamics is actually the study of energy and its interconversions, okay? So if you think of the word energy, there are many forms of energy, and this energy can change from one form to another. And what we're trying to do is we're trying to understand when energy changes between these different forms, what exactly happens. We're trying to understand the interplay between these forms, and that's the study of thermodynamics. So you might have heard of different types of energy. For example, kinetic energy is the energy of motion. You might have heard of that. Potential energy is the energy of a body that has the ability, the capacity to do work. So in thermodynamics, we will use these two forms of energy a lot, kinetic and potential. We use that to define certain systems, and then we'll go from there. And there are other forms of energy that you might have heard of, like thermal energy, okay, which is the energy related to the temperature change of a body. Then there is chemical energy. And chemical energy is the energy related to the bond structure of molecules. Now, within atoms itself, chemical energy is the energy related to the arrangement of electrons, protons, neutrons, and so on. Okay? All right. So that's kind of the big picture of energy. And now what we'll do is we'll zero in on the kinetic and potential energy aspect and try to understand holistically what does energy do. Okay? So what we need to understand is energy is really two things. Number one, it's the capacity to do work. Because why do we need energy? And why do we want to study energy? We need energy, we want to study energy because energy is the capacity to do work. Okay? And we are very interested in work. Okay? Another thing to understand about energy is energy also relates to the transfer of heat, okay, okay. So if you really get down to the nuts and bolts of energy, we are interested in the work that it can do, and we're interested in the amount of heat that can be transferred as a result of the work done or as a result of the change in energy of something that we're studying. Now let's try to go ahead and define work. So work can be thought of as equal to, I'm going to erase this little underline, is equal to a force when it acts through a certain distance. That's really what work is, okay? So if we call work, we represent work with a small w and a force with a capital F, work is equal to capital F times small d for distance. That's kind of how we can kind of express work, okay? And heat can be represented with a small letter q, okay? That's kind of the way we represent work and heat in thermodynamics. Okay. Now, before we can go any further, we need to understand exactly when we talk about work and heat transfer, we need to understand with respect to what, okay? So we need to define a system. So for example, let's say you are in a lab and you're trying to study a chemical reaction. Your system might be the chemical reaction that you're trying to study, okay? And then let's say you're performing this chemical reaction in a beaker or a flask of some sort. The chemical reaction ends up giving off a lot of heat. Well, where is the heat going? The heat is going into the surroundings. So it's important for us to define the system and then understand that there's always surroundings, and the work and the heat transfer, this interplay, this movement of energy is always happening between the system and the surroundings, okay? So two important concepts out here. We need to define the system. That is what we are trying to study. Okay, we're trying to study the system. And then the system is going to either absorb energy from the surroundings or release energy to the surroundings. So I'm going to represent the surroundings with another box out here. Surroundings. And so you can have energy being transferred from the system to the surroundings or from the surroundings to the system. Okay, so what's important to understand is when after we define the system, we need to understand exactly how much energy does the system contain, and that is defined as internal energy. So that's the energy integral to the system, okay? So internal energy is defined as, so once we know what energy the system contains, we need to figure out how does it relate to all the different energies we listed a few minutes back. So internal energy is typically defined in terms of, it is the sum of the kinetic plus the potential energies, okay? Kinetic plus the potential energies. Okay, so for now, we'll keep our definition that simple, okay? And what we'll do is we'll try to just understand when a system undergoes a change, then there's going to be a change in energy. So let's say a system does work, there's going to be an energy transfer, okay? So every system is going to have what we say is an initial state, and we represent the energy of the initial state as, let's call it E. So that's the internal energy E, initial. Let's call that. Let's put a subscript out there for initial. And then you can have, once the system undergoes the change, you're going to have a final state. And the energy of that final state is represented as E, final. So the change between the final and the initial state is going to be represented as delta E. And we're going to call that delta E system. SYS stands for system. And what this represents is the change in the energy of the system as it goes from the initial to the final state. So that should be the final, E final minus E initial. Okay? Now, it's important to note that this change in the energy, where did that energy go? So let's say, for example, the E final to E initial is equal to a negative quantity. Okay? What that means is that as the system went from initial to final state, the final state has lower energy than the initial state, okay? So if we kind of represent that with a energy level diagram out here, I'm just going to try to draw a little graph out here. I'm going to call that delta E system. So the initial state is going to be, I'm going to just, instead of writing it out there, I'm going to say, well, there's the initial state and there is the final state, okay? So as you can see, the initial state is higher than the final state. So if we take the final, which is a smaller number, and subtract the initial, which is a larger number, you will get a negative quantity. That's why we said negative quantity. So the final state is lower in energy. So where did that excess energy go as the system went from initial to final? That excess energy goes to the surroundings, okay? So coming back to this, I'm going to just create some space out here. If delta E of the system, delta E sys, we're going to call that, if that is less than 0, which means it's negative, right? If it's less than 0, then guess what? The surroundings gain that excess energy. So delta E, I'm going to represent surroundings as SURR, is greater than 0. Okay? By how much? By the same amount that the system lost. Okay? And conversely, if this ends up being a positive quantity, then guess what? Delta E system is greater than 0, which means if delta E system is greater than 0, then positive quantity means the system gained energy, which means it had to take the energy from somewhere, which would, in this case, would be the surroundings. So the surroundings would have lost that same amount of energy. So delta E surroundings is less than 0. Okay.